This is Lab 4 Circuits by Chandler Pittman. So a little bit about our table of contents today. First, we're going to talk about the introduction, which is like the purpose, the experiment, the equations used. Then we'll get into the second point of charge and energy conservation in series circuits, which will then get into RC circuit, and then finally our analysis and conclusion. So first, our introduction. So, a little bit about our introduction. What is the problem we are trying to solve? We're trying to predict how resistors will react in series and parallel circuits. We want to measure values of the current and the potential difference in circuits, and we want to know the general behavior of ohmic resistors and capacitors. And why are we interested in it? It is helpful for explaining and understanding series and parallel circuits. When it comes to the equations we use in this experiment, we use the voltage law, which is the voltage of the capacitor plus the voltage of the resistor is equal to 0, as well as kind of an exponential decay within an RC circuit that can be seen below. And so just a little bit about the brief results of the experiment. I1 and I2 were both equal to 0.0204 amperage. Hypothetically, our R of 47 was expected of 47. Our R of 100 was expected was 100. Time to charge was 31 seconds. Time to discharge 38 seconds. And experimental RC was 11.75 seconds. So tonight again, the experiments, we have a first one, charge and energy conservation in series circuits. So in this first experiment, we created a series circuit with two 1.5 voltage batteries, two resistors, and two ammeters. And to calculate the prediction for I1 and I2, we did I equals V over R, which was equal to 0.0204 amperage. And the ammeter, when connected backwards, was negative. So after we created this circuit in real life using our tools, we measured a value of 0.01 amperes, whereas we expected a value of 0.0204 amperes. So while we expected there to be a current of 0.0204 ammeters, we only observed a value of 0.01. This could be due to lots of different reasons. Maybe the batteries were wrong, the wires were messed up, things of that sort. However, our measured value was 0.01 amperes. So when it comes to calculating our potential difference, the graph on the right can be seen. It slowly goes down from 3 volts all the way down to 0. And when we calculated R47, we had an R47 observed of 96 ohms. However, we should have expected 47 ohms. In the same case for R100, we observed 203 ohms. However, we should have expected 100 ohms. And this is just based off our simple calculations. And due to our observed current of 0.01, our resistance calculation is going to be off, as the expected current should be 0.0204 amps. So it should be smaller, and our results are double of what they hypothetically should be. So next, let's get into the next part of the experiment, which was the RC circuit. So when it comes to this next part of the experiment, our next part of the experiment was to create an RC circuit to observe how a capacitor changes. You can see the diagram of the RC circuit in the bottom left. And over to the right, we can see the time to charge. A 10 ohms bulb was 31 seconds. The time to discharge a 10 ohms bulb was 38 seconds. And for a 20 ohms bulb, the time to charge was 1 minute and 3 seconds. And the time to discharge was 1 minute and 18 seconds. So here we have a graph of the time constant of the circuit. It's basically a graph of the time in seconds versus the natural log of our voltage over our voltage naught. We can see it slowly decays down and has a slope of negative 0.0851x, which translates to an experimental RC of 11.75 seconds. And finally, let's get into some analysis and conclusion. So for analysis and conclusion, what if you did this lab with real circuit components, access the virtual circuit, and see if you can determine how it behaved differently from the real ammeter you used? Real ammeters have a slight resistance to them compared to virtual ammeters. They also don't behave the same way as a virtual circuit, since virtual circuits are in ideal conditions and real ammeters are not, which leads to problems. So there would be a slight difference with real ammeters having a little bit more resistance. And what if you were to do this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? The ideal model will predict the capacitor to charge instantly. This is due to the fact that there is resistance in real batteries, which is why it does not charge instantly. So a little bit about some assumptions and errors in this experiment. we kind of assumed we were in perfect conditions while conducting experiments, at least for the online version. There's no leakage. And in real life, that was not the case, which kind of leads to the next point of the battery voltage inconsistency and the faulty wires and resistance. Due to us using the same materials for making the circuit as previous physics classes, there's a lot of inconsistencies and problems there. And finally, we assumed there was no electric field in the wires, or that it was negligible, which isn't usually the case. So that could be another assumption that we made.